right, so thank you so much for braving the weather, which is getting, I guess, more catastrophic by the minute. I'm hoping we don't float away in the auditorium halfway through the talk. But we're really delighted to have Professor Jonathan Butterworth with us tonight. I first want to say a word about this series that it's a part of. So it's part of the Shulman Seminars and Lectures in Sciences and Science and the Humanities. This is the first one of this semester. Inaugurated in spring 2007, the Shulman Seminars and Lectures in Science and the Humanities aim to encourage and sustain dialogue and intellectual collaboration across the proverbial divide between the two cultures. The series represents a bold and exciting convergence of the arts and sciences, and so is fittingly named after Robert Shulman, who I believe is here, Sterling Professor Emeritus of Chemistry, Molecular Biophysics and Biochemistry, Senior Research Scientist in Diagnostic Radiology, and a Founding Fellow of the Whitney. An unwavering supporter of the integration of science and the humanities, Bob Shulman truly and fully embodies the spirit of this program. And Emily Coates and I, who co-teach the physics and dance class that's happening this year as a Shulman lecture class, are certainly thrilled to be associated with this. So thank you so much for this opportunity. The series is supported with the generosity of Richard and Barbara Franke. So now on to Professor Butterworth. John is the chair of the Physics and Astronomy Department at University College London. He grew up in Manchester. He went to Oxford for his bachelor's degree and his doctorate in physics. After doing that doctorate in physics, he went to work on the Zeus experiment, or actually maybe even started during the doctorate. He worked on the Zeus experiment, which is an experiment of about 450 people, quite a few people. It's at the Hera Electron Proton Collider at DAISY, which is an international lab that's in Hamburg in Germany. He worked there first as a postdoctoral research scientist, and actually he was working officially for Pennsylvania State University. And you can read in the fantastic book that he wrote that I'll mention soon about some of his early trips to the US and what that was like as a young physicist coming over here to work for an institution but actually be based at an international lab in Germany. It's not an uncommon thing in our field. So he worked with Pennsylvania State University and then joined UCL as faculty. He was able at this electron-proton collider to probe the content of the proton, and he's credited with the first measurement of the photoproduction of hadronic jets. He moved to ATLAS in around 2006, 2007, and one of the initial things that he did that was incredibly helpful for the ATLAS experiment was take the data that we had from Zeus about these hadronic jets and apply them to the Hadron Collider, where basically most of what we have is jets. So we're all very grateful for that transitional work. We learned a lot about the proton itself and the different constituents of the proton and how much energy they carry when the proton is traveling at different speeds. So this is an excellent way that different experiments actually piggyback on each other. These large experiments, Zeus is 450, Atlas is about 3,000. They have a lot of internal structure. And John has had a lot of leadership positions inside of these experiments as he's gone on. He was the physics chair within Zeus from 2003 and 2004, which is really overseeing the physics program, which is an excellent way to get an overview of many hundreds of analyses that are ongoing. And then when he came to Atlas, he started out with the Atlas Monte Carlo group, convening that from 2007 to 2009. That's looking at our simulation across the experiment. And then became the convener of the Standard Model Group from 2010 to 2012. He was the convener of that group when my group was working on a standard model analysis, so we had a little bit of interaction through that. He also has done some work at the borders between experiment and theory. So John received the Chadwick Prize from the Institute of Physics in 2013 for some of this pioneering work. He wrote what he called the Jimmy program, and he defends that name, though it doesn't really tell you what it means in the book, which is interesting.
It doesn't mean anything.
Right, doesn't mean anything, okay. But it actually simulates multi-parton collisions, which is incredibly important, and we used it very heavily in Run 1 of Atlas when it was turned on. John has a science blog. A lot of people have science blogs, but John happens to be hosted by the Guardian newspaper, so he has a large readership for his blog. And as I mentioned, he wrote a book, Most Wanted Particle, about the Higgs discovery. It's a fantastic book that's personal, it's humble, and it's jam-packed with accessible physics, so I highly recommend it. We asked John to be part of this lecture series because of the many things that he's done. He's an accomplished researcher in particle physics, a collaborator of mine on Atlas, who I'd had some interactions with, and also because of his interest in outreach in science, and he's thought deeply about the process of research. And throughout this lecture series, where we have physicists coming and also dance artists and choreographers coming, we've really asked them to talk to us about what is the process of discovery in your field, what does it look like in what you do. It's something we're examining in the class. So thank you very much for coming, again, braving the weather, and please help me welcome Professor Jonathan Butterworth.
Thank you. Thank you very much, Sarah. And it's a real pleasure and an honour to be here. It's the first time I've been to Yale, and it's the first time I've actually given a dedicated interdisciplinary lecture between the arts and humanities as well, and I think it's a fantastic thing to be asked to do. Thank you very much. And that even includes the fact that I attended a physics and dance class earlier today, which was also very interesting and a lot of fun, so thank you for that. Yes, so this is subliminal advertising for the book in the background, but the title is Research at the Energy Frontier, What, Why and How. That's obviously quite a lot to get through in 45 minutes, and I'm really going to give you a flavour of it, but I hope there will be a few things that you'll learn and remember from this, some of them about physics and some of them maybe about how science interacts with the public and via the media. So this is where it all happens. This is where Sarah and I do our science now. This is the view that I got from the aeroplane window, if I was lucky, about twice a week while the Large Hadron Collider was starting up. What you're looking at here is you're flying over the Jura Mountains, which are in the kind of the east of France towards the south. This is Mont Blanc, which is the highest peak in the Alps on the horizon, and this is Lake Geneva here. And this will be Geneva Airport, where I would be either leaving or arriving at. The bit you won't see, of course, because the French farmers would have objected if we tried to paint it, but this is the path of the Large Hadron Collider. It's marking the path of a tunnel underground, which is 27 kilometers around. And inside that tunnel, we have the highest energy particle beams that humanity's ever managed to sustain and create and focus, and actually they've got two of them going in opposite directions, and we bring them into head-on collision at 4 points on that ring. And I guess that's high energy physics at some level, and this is the energy frontier now. And I'm going to tell you something about the kind of sociology and the physics of what went on there. The 4 points that the beams collide at are marked here. There's one of them here, LHCb, Atlas. This is the main CERN lab here. And you can see some of the previous high-energy machines in the world, which are now boosters for CERN, this blue ring here, for instance. And then ALICE and CMS over here. I'm going to show you data from these two, Atlas and CMS. Atlas is the one that Sarah and I work on. The other two are doing more specialist measurements, which are great physics, and I recommend it, but I'm not going to say any more about it here. There's a lot you can do when you have these beams. But what Atlas and CMS are doing is really exploring this energy frontier, and in particular, the Nobel Prize winning result that we got so far, although the prize went to the theorists, but never mind, was for the discovery of the Higgs boson. So I'll talk a little bit about that as a fairly well-known example of what, and I'll try and give you an example of what really happened. So one of the features of this is that it did feature in the news media and in the general consciousness, I think, here in the US. This is the second talk I've given. I gave a talk in a library in Chicago, and a lot of people seem to have heard something of this. And certainly in the UK, it had a bigger impact than many science stories ever do, which is in some ways surprising, because actually, does it really make any difference to people's lives whether we find the Higgs or not? Well, people seem to actually care about it. But one of the frustrating things about science in the media is you get a kind of 2-3 minute pop-up on some news channel, and basically all you've got time to do is say Eureka, and there's no build-up, there's no consequences, there's also the rest of physics for the past 200 years is probably news to the person interviewing you and to a big fraction of the audience. So it's really difficult to, you always get, the news is always right on the frontier, so it's always the stuff that actually you probably don't know. It might be gravitational waves. The neutrinos are probably not traveling faster than the speed of light, but those are the things that people would like to know about, and we may have found the Higgs boson or we may not yet, kind of thing. You'll see that we have now, but this is while it was being developed. So it's always good to try and connect it back to basic physics, and actually today I'm even going to try and connect it back to the dance class, because there's one question you can answer, which is, why is it so big? Like, why, if I work in London, now London, there's a reasonable amount of money in London, why do I have to go to CERN, to Geneva to do my work? Why don't we have one at UCL? Or why does Sarah have to go all the way to Europe to do this? And the reason for that is because it's very big, which means it costs a lot of money and it's very hard to build, so it makes sense to pool resources and only have one. But then why is it so big? And the answer, the reason it's so big is actually Newton's third law, which was mentioned today. These are the highest energy beams of particles we've ever had. They want to go in a straight line at constant speed more than any other particle we've ever had. That's what will happen to particles if you've seen Gravity, the movie, for instance. They get some of that wrong, to be honest. But things in space will just keep moving. The reason if we throw a ball, it doesn't go in a straight line forever because of gravity acting on it, and because in the end, if there was no gravity, then wind resistance would slow it down. Nevertheless, without those forces, it would keep moving. So, and we were studying friction in the dance class today. If I started sliding, I would just never stop. If it wasn't for friction, I would carry on going in a straight line. Bodies will do that. That's Newton's law. So these particles want to go in a straight line more than any other particle we've ever had in a lab. That's what it means to say they're the highest energy beams, the highest momentum beams we have. So the thing that sets the limit is, can you persuade them to go around a corner? It's not how much energy can you pump into the beam, actually. It's can you persuade them to go around the corner and come back again and actually hit each other and be stored in the ring. And the things that set that limit then are two things. How strong is the force you can exert to make them bend around the corner, and how sharp is the corner? This is why on a freeway the corners are narrow. The corners are very gentle, and a right angle corner on a road you have to slow down, especially in this weather, to go down. So this is where friction comes in, right? So the thing that turns your car around the corner is friction between the wheels and the road. And that's the force that acts and will bring the car around the corner, and you feel yourself being thrown out of the corner, but the friction will keep you on the road unless you go too fast. And in the end, the thing that limits how fast the car can go around the corner is the friction, the maximum force that can be exerted, and the sharpness of the corner. And it's exactly the same with the LHC. So it's not friction doing it, it's a magnetic field that provides the bending force. So we build the most powerful magnets that we can build, we know how to build, that bend the beams. And then the thing that sets the limit on the energy is how sharp is the corner. And if you want a very gentle curve, unfortunately, you need a very big ring. So 27 kilometers is done. So it's an optimization between the geology of Geneva, and can you dig a tunnel, the expense, will the taxpayers fund it, and then how powerful the magnets can you build, and then that tells you how high energy the beam will be. So that's the car. You know, if the beam skids off the road, it's very bad news, so we don't do that. So I'll say a little bit more about the organisation that built this. These are the member states of CERN as of now. The ones coloured in blue. The latest one to join was Israel, which is down in the corner here. And it was set up in 1954, just over 60 years ago, to try and help rebuild basic European science after the disasters of the Second World War. And of course, one of the disasters of the Second World War was that practically every physicist was in America at the end of it. They all came over here. So there was a way to try and build up collaboration across the borders and basic science again. The UK, despite the UK's grumpy attitude to Europe, it was actually in this from the beginning and has stayed in it ever since. It was one of the last things Winston Churchill did in his final term as Prime Minister, was to sign the deeds that said, OK, it can be in Geneva, we don't mind. And we've been in it since the middle there. That's where CERN is. And it's been a kind of fed at the level of about 1 billion currency units, Swiss francs, dollars, something like that, a year, pretty constantly for the last couple of decades, which is a lot of money, and it adds up. But it's spread out over all the European taxpayers. And the great thing is that it's cumulative. You saw that on the map I showed you, the old machines are actually now the injector stages of the new machines, and that kind of build-up of technology and expertise there has really helped. So to the extent now that everywhere, okay, Africa was supposed to be grey, but everywhere that you can see on here has some collaborative arrangement with CERN, ranging from formal observer status, or applying to join, or down to just sending some PhD students, exchanging students with the CERN things. So it's now really the place where the world comes to do energy frontier physics. The blue ones are still member states here. There's a member state in South America here, but it's actually France. It's French Guiana. It's where they launched the Ariane rockets from. So, okay, so that's the organization. This is the experiment. So on the ring, I said the beams are brought into collision in four places, and two of them are ATLAS and CMS, which is where I'm going to talk about the data from that. This is a picture of the ATLAS detector. So you've got to imagine one of the beams coming in that way, one of the beams going that way. They cross in the middle here, and some of the particles collide there. And the game is to record what happens in those collisions as accurately as possible and as quickly as possible, and try and work out what was going on in the heart of the collision from that. So you can see there are sort of concentric cylinders, different technologies, telling us different things about the particles. They tell us, how fast they were traveling, what their energy was, sometimes what kind of particle they were. I'm not going to say any more about this now, or there's a lot one could say, except to point out it's quite big. These are people here, if you hadn't spotted them. So it's a huge piece of apparatus, bigger than CMS, although not as heavy, apparently. So everyone has their superlatives in particle physics. The CMS are the heaviest, the CHIN, and we're the biggest detector. This is a picture of it that some of you, has anyone seen this picture before? One or two nodding, yeah. It's one of the, it's from 2005 actually, while we were building the ATLAS detector. This is one of the people building it. And I give talks in classrooms and various other places, and very often in England, this would be on the wall in the classroom, just in a general science classroom for kind of 13-year-old children. Just because somehow it caught people's imagination. It appeared, my dad is actually a priest, and this even turned up in the Church Times, which is kind of his work mag. It really had a kind of depth of penetration that I didn't expect my physics experiment to do when I became a physicist. And I think that was a sign that people were generally interested in it. This was in 2005. We were trying to engage people. And actually, when we switched on the beam for the first time, we had journalists in the control room, which was unheard of. I mean, people really didn't want... The standard thing in science is to do all the difficult stuff and then emerge triumphantly shouting Eureka and show everyone how clever you are. We didn't do that. We actually had people in there while we started the machine up, and in the book I described how tense that was at the time, and it was really, really interesting to be on live TV and actually still be more nervous about your experiment starting than you were about being on live TV, even though you've never done it before. And it was a lot of fun. It was very positive. People were really interested. But I think it's important to point out that it wasn't all fun, and it's often you get people being, you can see I'm not really having fun there. People, when you decide, you make a big decision when you decide to do science in public or not, and it's all kind of irrevocable decision. So you have to, if you're going to tell people how great your experiment is, you have to be prepared that some of them will say, well, that's not very great, you're going to destroy the world, which is what this guy thought we were going to do. This was when we were switching on these beams. The people were, one or two essentially eccentric or actually bad, evil people who were, not evil, but attention seekers who were trying to deliberately scare people. I could never make my mind up whether they were actually deluded or cynical about what they were doing, but it was very harmful, whatever. So I was in Geneva just before we were in the build-up to switching on, and I got a call from Al Jazeera, who are based in England. They have an English base and an Arabic base, and they're based in London. And I'd done some things with them before. They called me up and said, can you come into the studio and talk and do an interview with us, because the guy from CERN has just cancelled. Now, I should have thought, why did the guy from CERN cancel? We're in Geneva. Why are they calling me? But anyway, I said, sure, and I went along. And it was this guy, who's a guy called Otto from Tübingen, German guy, who's a theoretical biochemist, although I don't think that really means anything, who was the one scientist in Europe who was convinced that we were going to destroy the universe when we turned on the machine. And so I wasn't actually in front of the lake. I was in a dark room under an industrial estate somewhere on the outskirts of Geneva with a thing in my ear and a bright light in my face and no view of anything else. And I wasn't very happy about this. And it was terrifying because also it wasn't live. And you might think that live would be scarier, but it's not. It's really scary because if it's not live, you're at the mercy of the editor. And if you say 9 sensible things and 1 silly thing, they can choose just to show the silly thing. I was very worried about it, actually. Anyway, I did the interview, had no choice then. And when I saw it in the end, I really learned a lesson, I think, about once you started talking to people, the public about your experiment. First of all, the editor did a good job. He gave a fair impression of the interviewer, and it was pretty obvious there was only one mad scientist in the room, and it wasn't me. But the other thing is Al Jazeera really has a different reach from the BBC, and there were people in the developing world that they reach who were actually genuinely scared about what was going on in Geneva, and the feedback they got from this was so overwhelmingly positive, they were kind of stunned. So I think you've got to realize, it's very frightening for scientists because you lose control once you go to the public, and you have to accept that, because if you've invited the media in, and then you try and control them, then the backlash will be huge. You just have to invite them in and be honest, and that's really what we tried to do. And we even did that when we blew it up, which was pretty bad as well. 9 days after we switched it on, we had a catastrophic helium leak, and we destroyed it, an eighth of it practically. It set us back by 18 months. It was a dreadful time, especially for the PhD students who were just starting at that point. But that's what happens when you do research, and in the grand scheme of things, it really showed that the thing hadn't been stage managed, that we really were showing people a real event, not some kind of faked tension. You know, we were actually terrified and elated when it did work, and then devastated when it didn't. And then we came back 18 months later and it did work. So it gave a much truer impression of what research is really like as well. And it would have been awful if we'd have all just retreated into our shells again when it went wrong, but we didn't. And we even put up with people calling it the God particle and all kinds of ridiculous stuff. So that's a kind of detour into the science, the experience of doing science in the glare of media spotlight, if you like, which was not something we expected, and not something we're really prepared to deal with, but I think overall was a very positive experience. I'll go back to the science now. So this is a view of one of the collisions of of a pair of protons in these two beams that we're bringing into collision many, many times a second. And these are three angles, three representations of the same collision. So this is a slice through the cylinder, obviously, so you see the circular thing, and you've got to imagine one of the beams coming from the back of the hole, the other one coming from behind the screen, and they collide in the plane of the screen. And you see that there's grey. The grey stuff here is kind of not very interesting, low energy stuff. In fact, you can tell it's low energy because it's being bent by the magnetic field we have on here, and the force, back to the car going around the corner, the force is enough to bend the particles, so they're not very high momentum. Whereas these two guys, the yellow ones, are very high momentum because they've hardly been bent at all by the magnetic field. Also, by the fact that they punch through all the different layers of detector, we can tell that they're muons, which is something I'll come back to in a moment, but that's a heavy version of the electron. So it's often, there aren't many muons around in nature, so it's often a sign that something interesting happened. Now, if you look at this projection, this is the other slice through the cylinder, same collision, but with the beams going this way and this way now, and that red dot, and you zoom in on the red dot, this is what you would see. And you see that these particles are not all coming from the same place. Each one of those little ellipses is a source of particles that are flying out and that have been detected in the Atlas detector. And there are several of them. There are about 12 of them here. In fact, what that means is that the protons are not coming one at a time. And they're not coming continuously either. They come in bunches. They come in every 25 nanoseconds, we get a bunch of protons. A nanosecond is a billionth of a second. So every 25 nanoseconds, we get a bunch of packed with protons, as many protons as we possibly can, into the bunch. And they're very small protons, so most of them miss each other completely and go around and have another go. But some of them will collide, and in this case, about 12 pairs of protons collided. Actually, the way we were running at the end of the year, it's more like 60 or so, or even more. How was it piled up? Was it about 60 on average? Yeah, it's a lot, but we went to shorter bunch spacing, so it's a lot going on in there. And in fact, we're only interested in the ones that are produced here, so all the rest is noise as far as we're concerned. We want to get rid of it. So you have to pick that out. And as a physicist, I'm not very good at remembering numbers, but one I do remember is the speed of light, which is 3 times 10 to the 8 meters per second, which is actually about 30 centimeters, about a foot per nanosecond. Okay? Now, the fastest these particles are traveling is the speed of light. Some of them, they're all at that or below. So they don't have time, if you think about it, to get out of that huge detector. The detector is 50 meters long. And then you have to get the signals down the wire, and that can only go at the speed of light as well. So these are coming every 25 nanoseconds. We have another spray of particles, and another, most of which we don't want anyway, we just want these guys. And so that kind of data processing challenge is absolutely huge, keeping them all in time so you know which ones belong in the same time window as each other, joining the dots to make the tracks, deciding whether you want to keep this event or throw it away, and which ones you want to focus on, because you don't have time or storage space to keep them all and analyze them all. So that all goes on in a kind of office block full of computers just next door to the Atlas experiment. And then it gets farmed out around the world on a kind of cloud or grid of computers. Big data centers. There's one in Chicago, there's one in Brookhaven, I think, right? In the US, we have one in Oxfordshire in the UK. All the major collaborators have them, so that gets spread around, and then in the end it ends up on our laptops, and we do physics with it. That's how it works. So that's the sort of infrastructure you need in order to do this science, sort of in an overview form. And I told you why, if you want high energy, it has to be so big. But I haven't told you is why high energy is at all interesting. What's the point? Why are we doing all this? And there are several ways people like to answer that question. You hear it called the Big Bang machine, and you say we're studying the physics of the early universe, and there's an element of truth in that. I can answer questions on it afterwards if you like. But the way I like to think of it is what we're doing is actually we're studying the structure of matter, of nature around us. So we're not looking at the nature of the early universe, we're looking at what's happening now. What are the things around us made of now, with the highest resolution we can. And in that context, you can sort of think of the LHC as a big microscope. And I'm going to demonstrate this with an absolutely super high-tech demonstration, which is actually just a ripple tank. A mate of mine in Bonn made this video. So you've got to imagine, you're going to see ripples, waves in the water. You've got to imagine the waves are a beam of protons, and they're probing another proton. Okay, and this is the Atlas detector. This is a beam of protons. And someone's going to put a blob in there, which you've got to imagine is something that's inside the other proton. So they put this blob in. And now the Atlas would tell that blob's there, because the waves are distorted here. You could analyze the pattern of waves on the screen here, and you could definitely tell the blob was there. You could probably tell how big it was roughly, maybe even something about its shape if you did a really good job. Now they put another blob in, and it's completely invisible. The waves have reformed by the time they get to the screen, and you don't see it at all. If all you're doing is looking at the waves here, you don't see it. Now what happens? Crank up the energy. The frequency goes up, the wavelength goes down. Now you could see it. Okay? You could now tell the blob was there by detecting the pattern of waves on the screen here. And that's what we're doing. There's a very deep correlation within physics, of which this is sort of a faithful analogy, that if you go to high energy, then what you're doing is going to faster vibrations, and that means going shorter wavelength. If you want to see something, then you need a wavelength at least as small as the thing you want to see. So, for instance, if our eyes were sensitive to radar, then they would be great for seeing ships and planes, but I wouldn't be able to see you because the wavelength of radar is a couple of meters or something, whereas you're smaller than that. So the waves would reform. I would never see radar waves scattered off of you. Optical light's fine. It's a few hundred nanometers. It's pretty good for seeing small things. But if you want to see even smaller than that, then you need to go to X-rays, which are higher energy photons, or electrons, or in the end, something like the LHC. And what we're really doing with the high energies is we have the shortest wavelength microscope, if you like, for seeing the structure of matter. And we're looking, remember, not just inside the atom, we're looking inside the atomic nucleus. In fact, we're looking inside a proton. And inside the proton are quarks, which, as far as we know, are fundamental. But that, as far as we know, is really important, because as far as we know just means how closely have we looked. As far as we know, there's nothing inside electrons and there's nothing inside quarks. But that means how good is your microscope? It's a statement that experimentally is only true as far as you've been able to look, and the LHC is looking more closely than anyone's ever managed to look before. What I've got on the screen here is a result of that, of not just of the LHC, but of all the experiments that have gone before, all the work into probing the structure of matter. These are the actors in the standard model of particle physics, which is our best theory for what's going on. And in that theory, all these things really are fundamental. They're infinitely small particles that are not made of anything else. The claim is that everything in the universe is made up of quarks here, leptons here, and then the forces between them. What you see on the screen is the whole story. Everything's made of that, and this stuff is not made of anything else. Okay? That's the theory. Now, that's only true insofar as we've managed to do the experiments to validate it, but it's definitely describes a huge amount of data very, very accurately. What you see here is an up and a down quark, which is what make up protons and neutrons. You see it, which are in every nucleus, every atomic nucleus. You've got electrons here, and then there's this neutrino that goes with them, which neutrinos are not really the topic of this talk, but there's a lot of them in this room at the moment. They come from the sun, and they hardly interact with anything. And then you see the whole thing is copied again. There's a charm quark and a strange quark here, and the muon, that with the particles that I showed you before, the heavier version of the electron, and it has a neutrino too, and the top quark and the bottom quark, and an even heavier electron, which is what Sarah's students were working on when I was the standard model convener, and an electron that goes with that. We don't really know why it's copied 3 times, but it is, and every one gets heavier, and we know there are no more of them. At least there are no more that look the same. There might be some slightly modified ones, but there's nothing else with a light electron, a light neutrino, for instance. And then they interact by the photon, which is what's coming out of here. What you're seeing me with is the carrier of the electromagnetism, and it's also light, electromagnetic waves. The gluon, which is what sticks the quarks inside the protons and neutrons. And then the W and the Z, which carry the weak force, which is really short distance, so you hardly see it in everyday life, except in some radioactive decays. It's the only force the neutrinos experience, and it's crucial, for instance, in making the sun work. But it's buried inside the nucleus. The range is so short that you don't see it unless you go to really high-energy experiments. And that's it, or obviously not quite it, because there's something going on in the background there. And there's a very difficult and easy question to ask, difficult question to answer, which I've asked me when I've given this talk in primary school. So like a 10-year-old child asked me the question. He said, how can something that is infinitely small and not made of anything else, how can it even be anything? How can it weigh anything? How can it do anything? And that's a very deep question, which actually was exercising the minds of theorists even before we'd heard of even before we knew that quarks were real or anything, in the early 60s. Because it turns out, as well as being a kind of conceptually difficult question to get your head around, that is also a mathematically very difficult question to answer in any kind of coherent theory. The theories we have that guide these forces are based on symmetry principles, and it turns out that the mass of a fundamental particle can actually destroy those symmetries and therefore destroy the whole theory. And that was a very a known problem even before we had the theory. It was like, yeah, but when you put this theory together, you'll have this huge problem when people were trying to put together the theory. Even when they thought that hadrons were fundamental particles, they thought it was a problem with them, and then they found out, oh no, they're made of quarks, so that's okay, because you can have mass if it's made of something else. The mass is to do with the binding energy of the things, and that's all okay. But if it's not made of anything else, that dodge doesn't work, and you're left with a problem. And 2 Belgian physicists called Francois Engler and Robert Brout came up with a way around this that worked mathematically. And a couple of weeks later, or in parallel really, publishing a couple of weeks later, Peter Higgs in Edinburgh came up with the same idea. And what it did was it filled the whole universe with a new energy field, a quantum energy field. And the mass of these particles actually becomes something they get by sticking to this field. Rather than something they have internally, it's something they get by sticking to this field. And that worked. It made all the mass work and everything. And that's, of course, this thing. You might wonder, since I said that Engler and Brout did it first, why it's got a big H on it and why it's called Higgs. And the reason for that is arguably a little unfair, but it's true, is that Peter Higgs' paper was a bit more explicit about how you might detect this field. So as a theorist, maybe just inventing this whole field and making the theory hang together is satisfying. As an experimentalist, I'd like a bit of evidence for what you've just done. I think it's quite a bold step to invent a new energy field that fills the whole universe, and just to make the maths come out right. So how would you discover it? It's rather difficult to prove that this field is there, to find evidence for it. Because you can't take one bit of the universe without the field and another with the field and compare them, because if it's anywhere, it's everywhere, so that doesn't work. And it turns out the way to do it was implicit in an equation. Well, it was implicit in all their work, but it was more explicit in Peter Higgs' paper. Is you actually hit that field really hard with something, and you make a ripple in it, effectively. It's a quantum excitation, but it's essentially a ripple. It's the equivalent of, how do you know that there's air in this hall? Okay? There are many ways, in fact, of knowing there's air in this hole. But if there were no air, if there was a vacuum in this hole, then not only would you not be paying attention, you wouldn't be able to hear me even if you were paying attention, because there'd be no way for the information to get from my mouth to your ears. And the reason it's doing that is obviously sound waves. What they are, you can think of as being an atmospheric field in the hole. What I'm doing when I speak is I'm exciting little ripples in that, and they transmitted through the air, and they hit your ears, and you detect them. That's a good analogy for what we can do at the LHC with this background field of the universe. We basically hit it really hard and make a ripple in it, and that ripple is a quantum excitation, so actually it looks like a particle, and that particle is the Higgs boson. So that's why we were so excited to find it. It's not like we've got a stamp album with a gap and we need a new particle to go in the gap. This is the evidence that this mathematical idea and this whole energy field that fills the universe is actually right. It makes a very unique prediction that if you hit it hard enough, then you should see this new particle. And it predicts what the new particle should look like. It doesn't actually predict how hard you have to hit the field, or not exactly. We knew enough to know the LHC would be able to do it if it was right, so it was a falsifiable theory in that sense. But it didn't predict exactly how hard. But it did say, well, if you made it, this is what it should look like. And that's what we kind of did. And I'm going to show you the data for that now. I'm just going to skip over these because that's not needed. So I'm running out of time. What time is it? Is that clock stopped? Okay. So what do we do in order to discover a new particle at the LHC? What we do, all we can do, right, is look at the pieces when we smash these protons together. It's a fairly crude, for all our technology and grand theories, it's a fairly crude approach, really. You smash things together and look at the bits. But you get predictions of what these bits are. So if you make one of these Higgs bosons, we have a theory that predicted the existence of it, also predicts what will happen to it once it's been made. It doesn't travel very far, unlike the sound waves in the auditorium here. It doesn't travel very far. In fact, when I say it doesn't travel very far, I mean 10 to the minus 20 something of a second is how long it lives, so it doesn't have time to get anywhere, really. But it decays into other particles, and those particles we can see, and we have a prediction for how they'll appear in the detector. They'll hit our detector, and we can measure them. So one of the things that it will decay to is a pair of photons, which is just light. It's just what you're seeing me with now, but very high energy light, much higher than optical light. The same stuff, basically. And what you see here is a pair of those photons, these yellow blobs actually registering in the detector, two very, very high energy photons. And you can make a hypothesis. You can say, well, there's lots of different ways, actually, you can make a pair of photons. How do I know these came from a Higgs boson? Well, I don't, actually. There's no way of telling even individually whether they did or not. But I can count them and look. And what I can do is make a hypothesis. I can say, well, let's pretend these photons came from a new particle that I just made, or one that I just made up, even if you're a theorist. Then what would its mass have been? And because we measured their energy and angle and everything, we can do a bit of relativistic calculus, kinematics, he says casually. You can actually do the sums. They're not that hard. You can add them back together, and you can work out what the mass would have been if they come from a new particle that decayed. And you can just plot that. You can count them. You can say, for every pair of photons, let's just count the mass, calculate the mass, and put them on a histogram, and wait and see what happens. And that's what's going on here. This is 2 years of our lives going past here, 2011 and 12. What you're looking at here is just what I said. So all the pairs of photons that we see in the LHC with these high energies. What's the mass of the particle that might have produced them if it really was a particle that produced them? And you can see there's lots of different ways of doing it, but you can see that there's a little concentration here. And that's what you expect if, in all the possible ways of making these two particles, I can leave it running. Go on, yeah. I like watching it. So I've watched this. You don't want to know how many times I've watched this. But you see that we're kind of rolling the dice when we crash these protons together. It's a quantum mechanical process. You don't get the same result every time. You get a distribution of probabilities. And you can see that there are a lot of photon pairs that are just in a smooth distribution. They're just made in all kinds of different random ways. And to find a little bump like this, which is actually at 125, roughly 125 times the mass of the proton, in fact. But you see, it's not there. I mean, there was all kinds of excitement about a bump down here at some point, and it goes away. You see the error bars are reflecting the statistical uncertainty, And you need to roll the dice more and more times. This is why we say, oh, we need more data, we need more data. What that's doing is shrinking those error bars down. And most of those bumps go away, but one of them doesn't, and that's what happens. Now, we announced this in 2012, and July the 4th, actually, in 2012. And July the 3rd, I was in CERN and watched Fabiola Gianotti, who's the head of our experiment then, who's now Director General of CERN, in fact, kind of give the presentation, that she was a practice presentation for what she was going to say to the world the day after about the discovery. And it was really the first time we'd actually seen all our data put together in one place, and it was quite amazing, quite an emotional experience. And I thought, yes, we've really got it. We've found the Higgs, and I know before, well, nearly anyone else, apart from the other 3,000 people on Atlas and another 3,000 on CMS, and Rolf Hoyer, who probably knew, was the Director General of CERN. But then I had to go back to London because I was head of the UK bit of Atlas, and not all the journalists could afford to go to Geneva, and the politicians didn't go to Geneva. But the science minister wanted people there, and we had a little press conference and event, and a lot of UK scientists turned up and watched the webcast of the whole talk and everything, which was, I'd rather have been in Geneva, frankly, but it was a good thing anyway. And I hadn't seen the results from CMS, which is the rival experiment. I knew they had something, obviously, there were rumours flying around, but actually seeing really what they were was really important. And Jim Verdi, who's the UK head of CMS at the time, who was also actually the spokesperson of CMS for a long while, was doing the equivalent job that I was doing for Atlas. He was doing it for the rival experiment. And we got there at 5 o'clock in the morning. We were going to be on the radio at 6 o'clock in the morning. We knew we were going to miss the presentations, and we were desperate to see them because he really wanted to see Atlas and I wanted to see CMS, and we hadn't been able to get them because they'd only been finished the night before, so we didn't know what was going on. So there's this moment when we sat down at 5:30 in the morning in this big hall in Westminster in London, and he showed me the CMS results and I showed him the Atlas results. And what surprised me was I got a real kind of thump to the gut that I thought I believed our result but I only really believed it when I saw this, which is the CMS had the same thing, which I think tells you something really important about science, that you do the best you can not to fool yourself, as Feynman would say, but it's only when someone else with a completely different set of people, set of politics, statistically independent data sample, and completely different detector technology comes up with the same result, then you realize you've really learned something about nature and not just about your own fantasy about what was going on. Now, this was really important. It's the same bump in the same place. I mean, I should have known because we also had other bumps. This is 2 muons and 2 electrons, which also is another way the Higgs can decay. And you see the black points of the data collecting. The red histogram is what life would be like if there was no Higgs. And you see there's a point here where the data diverges. We got excited about this for a while at one point. But you see here, there's a growing, you see kind of knowledge, fundamental new knowledge about the universe kind of growing out of this background chaos of statistical error, which I think is still rather beautiful. And if you zoom in on it, which you will do in a minute, and you put in a model of a Higgs boson, it roughly gets it right. We know better than, we can get it more right than that now, but it's telling you something. CMS actually did one where, same plot, this is the same distribution, but now for CMS, where the answer's in already. This is what a Higgs would look like. And again, watching the error bars shrink as more and more data come, and seeing that the data follow the red histogram, you know, with pauses and glitches and things that you get excited about and then disappointed about. And then, but in the end, you see that it works out. And that bump there, all of those bumps were in the same place, which tells you they're all the same particle decaying different ways in different detectors, but the same thing. We have much more other evidence for that now, and we're studying it. The properties match up to being the particle that was predicted in the 60s that was that is the ripple in this background field of the universe, and the background field of the universe is what gives fundamental particles mass. So now, in principle, our theory just works, and we can all go home and do something, dance or something instead. We'll dance as well, maybe. There's a lot more to it than that. I'm not going to spend very long on it, but I just don't want to leave you with the idea of physics as a kind of done and dusted, aren't we clever, it's all finished kind of deal, because it's definitely not true. There's a lot more we want to learn about the Higgs. Even when, I'm not going to go through all this, don't worry, but even whether there might be more of them, I don't know why this big one looks so worried, but there might be more Higgs bosons. There are various things showing up at the moment that might be hints of that. I also sort of lied when I said that all the universe is made of this and this is made of nothing else. In the theory, this is fundamental, and in the standard model, this is all there is, but we have very good astrophysical evidence that there's this stuff called dark matter out there that is actually the majority of mass in the universe, and we don't really understand what it is. There isn't an obvious candidate in the standard model for it. What I'm showing you here is actually, I'm head of physics and astronomy at UCL, and the astrophysicists always have to go one better. So we have the biggest physics experiment in the world. They do collisions with galaxy clusters. Right? So you can't beat that, really. These are images of galaxies, star clusters colliding with each other. And you can look in the optical and you see the stars passing by each other. You look in the infrared and you see the gas in the galaxy heating up, and you can see the emissions of that heating up, and the gas kind of collides and heats up, whereas the stars pass by because they're very sparse. And the question is, what if these things are actually 75% dark matter? Where does that go? Does it bang into itself, or does it just pass through? And it's dark, so it's transparent, actually, as Lisa Randall's trying to rename it as transparent, and she's right, really. It's not dark, it's transparent. But you can tell it's there only from its gravitational interactions, but we can use the way it bends light around it to actually map it out to some extent. And they've seen from these that the dark matter is more following the stars than following the gas. So it tells you that dark matter actually doesn't interact very much with itself either, which is something we didn't know a little while ago. I find it tremendously exciting that the astrophysicists are managing to learn things about the properties of dark matter in this kind of way, but it really makes me annoyed, and we really should actually make more of it at the LHC, and we might make more of it at the LHC in the lab and really work out what's going on there. But it's certainly a big gap in the theory. It's certainly a big unanswered physics question as to what most of the mass in the universe actually is. And finally, just for now, there are other questions as well that I won't go through, but we also don't really understand why the universe is made almost entirely, it seems, of matter. Because in the Big Bang and in the LHC collisions, we make matter and antimatter in equal amounts. And of course, when it meets, it annihilates, which is what the artist is trying to illustrate here. If you meet an antimatter person, do not shake their hand. This is clearly not happening in the universe around us, so we don't know where all the antimatter went, and the theory doesn't really accommodate it very well. So actually, the LHCb experiment, that's one of the main things it was specialized in studying, but there are other ways of looking at it. There are experiments in Chicago at Fermilab that are looking for evidence of why this happened, and we may learn something about it from ATLAS and CMS as well. So that was just a quick whistle stop. I showed you that bumps are important. This is a bump we don't understand yet. It may just be one of those that goes away in the data. This is a much higher energy than the previous ones at 2,000 times the mass of the proton. We don't know. We're watching it carefully. We had another one in the pairs of photons, which is the same distribution we found the Higgs in at lower masses. We have another bump here. Is that a real bump, or is it part of that statistical noise? We don't yet know. It's on the face of it, it looks quite real, but then we're looking at a lot of different things, so there will be some fake bumps, and we have to just get some more data and look. So it's still a very exciting time. It's been a fairly wonderful time to be a physicist the last few years. It's still a lot of excitement in the future. I put this up here just to show that we do have ridiculous dreams. This is the Large Hadron Collider, looking quite small compared to what might be next, if we think there's a point to it and justification. That's a view of it from the Jura. But it's not all just bigger is better either. This is an accelerator chip designed in Stanford, where you can actually get a higher accelerating gradient in that chip. That's a human finger that it's on. In that chip than you can in one of the cavities at CERN. The slight snag, is that you have to fire an absolutely enormous laser through it transversely, and then you'll get the electrons going that way. But if you can find out a way to do that, then you could build something of the energy of CERN in a few hundred meters rather than 27 kilometers. So I show that not because I think that's what we're going to do. It's something that's useful, but maybe for low energy things. But there are many other innovative ways that we're developing of processing the data, detecting the particles, getting the particles up to high energy, and that's going on all the time as well. So it's not just a matter of building bigger tunnels, but we have plenty of interesting physics questions to address, and lots of interesting technology options to address them as well, I think. So I shall leave you with that thought. Thank you. You've got more questions in your friction talk, that's it. Yep. The honest answer is I don't know exactly, but it's the output of a fairly major substation. So I don't know the number in gigawatts or anything, but not as much as the previous experiment that was there. So the previous experiment in the same tunnel had synchrotron losses, so it was losing energy. It was an electron collider, and then they used to they did a deal with the French power net grid, and they were not allowed to run it in the winter because of all the ski lifts and heating that was running. So it was significant on the level of the power usage of a city like Geneva. In that case, it's less than that now actually, because protons are not as energy hungry once they're up to energy, and there's a cryogenic system that keeps it with superconducting magnets that don't require as much input of power, but it's still very significant. But I don't know the number, I'm afraid.
When I say the motion is made of H2O, I can tell you lots more about this. When you tell me that everything is made of, what do you mean?
When everything's made of...
How does that tell you what to do?
How does it manifest itself? For instance, so first of all, the electron is obviously that's something we've known about for more than 100 years, and that understanding how electrons interact is how we understand H2O and chemistry at some level as well. So that level of substructure of the atom, which is the nucleus and the electron, is an important thing to understand from that point. That it's okay. Right. Yes. No. Well, the electron is a basic particle, so it's a fundamental particle. And what the theory tells us in that, so it's a very good point actually that it doesn't tell you the mass, and that's one of the questions I could have added as an unknown thing. So the Higgs allows things to have mass, but it doesn't predict what the masses will be, and whether there's a pattern to the masses. So in the periodic table, there's a pattern to the properties and the masses of the elements. That is kind of reminiscent of the pattern that we have of the fundamental particles, but there's no reason for it in our model, whereas in the periodic table, we understand it in terms of the substructure of the elements. So that's an open question. The quarks is a bit different, so understanding that hadrons are made of quarks really does tell you their properties. So you can work out their masses can be calculated using lattice techniques, and their spin and their charge, and all those properties are derived from the fact that they're made of quarks. So in that case, it does predict it.
The argument made for building this enormous thing is that it tells us a lot about the world. You tell me that the world is made of those quarks that
yes.
you have there. What do you mean when you say that the world is made of it? How does that tell me anything about this world?
It tells you...
including the bigs,
yeah.
which is sort of was
including the what?
Including the bigs now.
Yes. I'm not sure it does. I mean, the idea that there are fundamental principles and there are fundamental particles, okay? So the fundamental principle of things like symmetry breaking, for instance, the Higgs mechanism was developed a version of it was developed in condensed matter physics, and you see the same emergent principles that we're seeing in what we think are fundamental particles play a role in things like the properties of materials and stuff. So there's a really deep connection there between...
However, there are questions being raised by condensed matter physicists as to whether the breaking of symmetry came from there, or how is it helped in condensed matter when you talk about things to know that there's broken symmetry in particle physics?
Well, I think I would draw the distinction between... There are frontiers of knowledge, okay? So I think there's a valid frontier of knowledge, which is what are things made of if you look at them at the shortest distances we can access, which is what we're doing. There are also fundamental principles, which are equally fundamental. So fundamental can be used to say that it's a particle that's not made of anything. But I think something like spontaneous symmetry breaking, for instance, is a fundamental principle that is manifested in nature on many different scales. And I think there's a relationship, but in both directions. And I think there's a kind of frontier of complexity and emergent principles. There's a frontier of the kind of reductionist frontier of what things actually made of if you look closely enough. How they really inform each other is, I think, via these principles that emerge like symmetry breaking and stuff, where you see that there are behaviors in condensed matter physics that if we didn't know that electrons were fundamental, at least to some energy scale, we would not make sense. There are other ones that really don't care about that, actually, and that what we're learning at the LHC is completely irrelevant for, because the principle that the physics you're seeing is emerged at some much lower energy scale in a complex system. So I think I wouldn't claim this is the ultimate, I'm not a fan of kind of theories of everything, which says if you write it down an equation, suddenly you understand the whole world. That's, to me, transparently nonsense. On the other hand, it is valuable to know the Dirac equation is of use to people trying to understand electrons, and the Standard Model is of use to people wanting to understand the way electrons and atoms and things interact.
Thank you.
Yep.
So if you described, we're all bathed in this field, what's the term?
The Higgs field, I mean, the quantum, yeah.
Sometimes these things are mathematical constructions that make things work, and sometimes they really are things. And so I was
Only a philosopher could tell the difference.
struggling to understand whether this was a useful construction that enabled you to make both prediction and observation.
Yeah.
Or should I really imagine I'm sitting here in this field as we speak?
So, actually, following on from the previous question, what it's told us is that that principle of spontaneous symmetry breaking underlies that field, right? And that's what predicts the Higgs boson. In a way, you could, if you're not a fan of, if you actually don't care what the fundamental constituents of nature are, the fact that that symmetry principle has made a prediction of a scalar boson, which is what we've seen, is a really deep, it tells you there's some reality in that maths. It tells you that nature really does care about that mathematical principle in a way that is actually really mysterious, right? There's no reason it should, but that was done purely through maths and predicted something we can see and reproduce in an experiment like ours. To me, is entirely wonderful. And it actually, going back to the previous, I don't really care whether the Standard Model is the inner layer of the onion or whether there's more to find. I'm fascinated by the whole process. But it's really something startling that even if the Higgs is not a fundamental particle, even if quarks and electrons turn out to actually have some internal structure, at this scale of nature, that mathematical symmetry principle that was invoked to make the theory work made a prediction that is actually realized physically. That is really wonderful to me and will stand, whether the Standard Model turns out to be another low-energy effective theory or not, that will stand. That prediction worked, that maths had some reality in real physical nature. That's stunning. Any more questions? Thank you very much.